Video games with heavy modular capabilities typically share a core architectural flaw. They rely on runtime resolution. When you load dozens of discrete modifications into an engine, you are crossing your fingers and hoping they fit together. A standard modpack is just a folder full of independent files. There is no central authority verifying the links between them. If one module requires a specific function from another, it blindly assumes that function will be there. Because these links are implicit, missing components, broken code, or conflicting operational roles remain hidden while the files sit on your hard drive. The only way to find out if the system works is to launch the engine and watch it try to initialize. In enterprise software, waiting for a system to boot to see if it crashes is an unacceptable standard. Mission-critical environments validate their dependencies long before execution begins. Relying on the game engine to sort out implicit dependencies at runtime cannot scale for massive modular ecosystems. The solution requires a shift to pre-launch deterministic validation. The Echo native platform replaces the traditional folder of discrete files with a verified, contract-driven operating system known as PackOS. Echo achieves this stability by running the operational report slice. This is a strict, deterministic pipeline but executes entirely before the game engine is allowed to boot. The pipeline operates in 4 consecutive phases. First, workspace scanning, followed by graph building, then diagnostic aggregation, and finally, readiness evaluation. Its strict purpose is to prove the integrity of the entire system without ever launching the underlying Minecraft or Neoforge environments. By forcing all code validation to happen statically, Echo guarantees that massive collections of independent modules will behave predictably. The first phase of this pipeline relies on the workspace and metadata scanners, which ingest the raw files of the repository. The scanners specifically target the echo.mod.json and echo.ai.json metadata files located inside every individual module. From these files, the system extracts precise module identities, required operational roles, API stability levels, and specific AI routing links. If a primary metadata schema is missing, the scanner engages strict fallback behaviors. It infers identities and versions from secondary sources, like Gradle.properties files, rather than crashing the pipeline. This extraction process converts the raw repository into a normalized, machine-readable inventory. You cannot build a deterministic graph out of unpredictable, unformatted inputs. Normalizing the data is the mandatory prerequisite for mathematical validation. With the data normalized, Phase 2 maps the workspace into a directed acyclic graph, or DAG. In Echo, this is called the module graph. In this chart, the nodes represent individual modules. The connecting lines, or edges, represent direct relationships, indicating whether a module requires, optionally supports, or strictly conflicts with another. By plotting these relationships, the system catches trust-level violations instantly. If an unofficial module loads into an official pack, the graph flags the unauthorized connection. Graph traversal also mathematically detects dependency cycles. If module A requires B and B requires A, traversing the graph reveals the infinite loop that would cause a runtime crash. The module graph resolves basic architectural logic. It mathematically prevents dependency hell before the user ever hits play. While the module graph prevents basic crashes, relying exclusively on hard module-to-module dependencies is too brittle for a scalable framework. To solve this, Echo utilizes a feature graph, structured mathematically as a bipartite graph. Here, modules do not depend directly on other modules. Instead, they interact with an abstract middle layer. Modules on the left provide features, and modules on the right consume them. For example, the Echo Ashfall protocol pack does not explicitly require the Echo terminal module. It simply requires that some module within the system satisfies the terminal.surface feature contract. The graph's validation rules scan for exact matches. It flags an error if multiple modules attempt to provide the same exclusive feature simultaneously, or if a consumed feature has no active provider. Decoupling dependencies through this bipartite abstraction allows developers to seamlessly swap out components and refactor architecture without breaking the core system's stability. Once the graphs are plotted, Phase 4 translates any recorded violations into actionable data. Traditional error handling often dumps a raw, opaque Java stack trace onto the screen, leaving developers to guess the root cause. Echo replaces this with the diagnostic aggregator. The aggregator compiles all graph errors into a unified diagnostics.json file. This document explicitly defines the severity of the failure, the affected feature, the exact module owner responsible, and provides machine-actionable repair commands. Deterministically mapping errors into a structured JSON schema converts a fatal crash from a manual debugging exercise into an automated, routable repair task. The final milestone of the operational reports pipeline is the Pack Readiness Evaluator. This evaluator takes the aggregated graphs and diagnostics and compares them against a specific PackOS profile requirement, such as the standard variant of the Ashfall pack. The result is the packreadiness.json report. It yields a final binary status verdict. The pack is either ready, degraded, needs repair, or blocked. This single status represents the culmination of all prior static analysis. It provides a definitive go or no-go state, requiring zero runtime execution to verify. Because this readiness status is generated statically as a lightweight data file, it can be consumed by external tools entirely outside of the game client. The Echo launcher reads the report to physically prevent unsafe boots and display clear health metrics to the player. The command center parses the exact same data to auto-generate one-click repair plans based on the diagnostic schemas, and the CyberDex bridge reads the output to dispatch context-aware, highly targeted bug-fixing tasks directly to specialized AI agents. PackOS replaces implicit runtime dependencies with an explicit, graph-validated architecture that is verifiable before the first line of game code executes. The operational reports pipeline ensures every component is contractually sound, providing a deterministic foundation for the entire game ecosystem.